topic for today is matrix multiplication. If we want to multiply a matrix by another matrix, we have to check the dimensions first. Basically, a matrix has rows and columns, and when we declare the dimensions of a matrix, we always start with the number of rows and then we mention the number of columns. Therefore, a 3 times 4 matrix is 3 rows and 4 columns. If we want to get the matrix product, the order of the two matrices matters, and the dimensions have to match with each other insofar as the number of columns of the first matrix has to be the same as the number of rows of the second matrix. Only in this particular case we can multiply them. So if we have a 3 times 4 matrix and a 4 times 1 matrix, we can build the product and get a 3 times 1 matrix. Why? Because the resulting matrix has the same number of rows as the first matrix and the same number of columns as the second matrix. Another example would be a 2 times 2 matrix and a 2 times 3 matrix, which leads to a 2 times 3 matrix. Remember, the outer numbers are the dimensions of the row matrix, of the new matrix, and the inner numbers have to be the same. As a counterexample, we can have two matrices even with the same dimensions, for instance 2 to 3 times 2 matrices, but we can't build a product out of them. Principally, if we have an m times n and an n times k matrix, we can build a product and we get an m times k matrix. Now we'll have a look at a numerical example. Assume two matrices, a 2 times 3 and a 3 times 2 matrix. From our previous considerations we already know that we can build a product and the result is a 2 times 2 matrix. Now we take the first row of the first matrix and we form the product with the first column of the second matrix, as if we would form a scalar product of two vectors. So let's start. We take the first element in the first row of the first matrix, which is 1, and multiply it with the first element in the first column of the second matrix. Then we add the product of the second element of the first row, first matrix, and the second element of the first column, second matrix. And finally, we add the third element, first row, times the third element, first column, to get the first element in our new matrix, which is 7. And then we proceed in the same manner. To get the element in row 1, column 2 of our new matrix, we multiply row 1 of our first matrix and column 2 of the second, which is 1 times 0 plus 4 times 3 plus minus 2 times 4 to get 4. Then, for the element with indices 2, 1, which means row 2, column 1 of our new matrix, we form the product of row 2, first matrix, and column 1, second matrix. That is 3 times 7 plus 0 times 1 plus 3 times 2, which is 27. and the same for last element. 3 times 0 plus 3 plus 0 times 3 plus 3 times 4, we get 12. Up next, we look at the formal definition of matrix multiplication. Let's say we have an m times n matrix A and an m times n times k matrix B. We multiply them to get C. Now we examine the coefficient Cij, that is, the element in the ith row and jth column of C. We get Cij as the sum of AIL times BLJ, where L goes from 1 to n. Remember, in our case, n is the number of columns of A, and also it's the number of rows of B. So essentially, the element in the ith row, jth column of our result is the product of the ith row of A and the jth column of B. In the end, we have some final remarks. You can have matrices with coefficients in any field, not only the real numbers. So, for instance, you can build a matrix product out of two complex numbers, out of two complex matrices, in the same way as we have already seen. Another important fact is that matrix multiplication is associative, which means there's no difference between A times B in brackets times C and A times brackets B times C. But it's not commutative, which means you can't interchange two matrices. Say you have a 3 times 4 and a 4 times 2 matrix. We know we can build a product and get a 3 times 2 matrix. On the other hand, if we take a 4 times 2 and a 3 times 4 matrix, they are not compatible. But what if we have two quadratic matrices A and B? You can build A times B and also B times A, but they can differ as the following example shows.